Hi there, everybody. We're now on our next video on number theory, and if you can recall in the previous video, we have talked about the theorem number 5, and where we could see the some illustrations of theorem number 5. So in this video here, right now, we're going to now define the Euclidean algorithm proper, okay? Or we're going to show you the mechanism or the algorithm itself, shall we say? So the Euclidean algorithm states that we'll first let a and b to be positive integers. So with a at least equal to b, at least greater than b, okay, or at least b, shall we say? So if a is equal to b, then the GCD, the greatest common divisor of a and b, is just equal to a, which is equal to b. So if this happens, if they are equal, so that's very boring to do. Okay, that's tedious. So we'll assume that a is strictly greater than b. So if this is not true, we'll just simply switch them, b to a. So one thing is it should be that the dividend, must be greater than the divisor. And then we let r sub 0 equal to b. Again, we let r sub 0 equal to b, meaning the remainder, the zeroth remainder, is equal to b. Then, by successive application of the Euclidean algorithm, the division algorithm rather, okay, by the successive application of the division algorithm, we get the following sequence of equations. So here up until and so on. We start with the original dividend, our a, and then again we let our b to be equal to r sub 0. So this is our b, our divisor. We will get a unique quotient and also a remainder. What happens here? So this is your quotient also. What happens here is what we'll do by theorem 5 is that the r sub 0, the divisor in this first equation, will become now the dividend in the next equation. And the remainder in this first equation will become the divisor in the next equation. And then we continue the process. Okay, the r sub 1, the divisor of the old equation, will become the dividend of the new equation. The remainder of the old equation will become the divisor of the old equation. And then this goes on and on. Okay, just take note that the previous remainder is always greater than, strictly greater than the new remainder. Now, what we'll do is continuing like this. Okay, if we're going to continue the process like this, we get the following sequence of what we call remainders. Okay, sequence of remainders. This will be shown as b is equal to r sub 0. So this is first the identity that we have taken into consideration, that b, our dividend, or rather our divisor is equal to r sub 0. So we say that r sub 0 is greater than r sub 1, which is greater than r sub 2, which is greater than r sub 3, which is all greater than or at least 0. At least 0. Okay? And now, since the remainders are all non-negative, clearly, and are getting smaller and smaller. As you can see, it's approaching 0. They're all approaching 0. This sequence should eventually terminate with remainder r sub n equals 0. So it should eventually reach r sub n, which is the last non-zero remainder, because r sub n plus 1 is the 0th remainder. Thus, the last two equations in the procedure above, okay, should be this. Okay, so the last two equations of the procedure should be this. So this is the last two equations. So the the second to the last equation should be r sub n minus 2, which will give us r sub n minus 1, then r sub n minus 1. Or rather q sub n minus 1 and r sub n minus 1 plus r sub n. So by the application of theorem 5, we will put the old divisor here and the new remainder here. Okay, actually this plus 0 is just, since it's r sub n already. So we will, we can just erase this if you want. It's okay. Therefore, r sub n minus 1 is equal to q sub n times r sub n, since there will be no remainder. It also follows by induction that the GCD of a and b is equal to the GCD of a and r sub 0. Again, the b is just equal to the r sub 0, I recall. And then this r sub 0 will become the dividend. The new remainder will become the divisor. So on, the old divisor will become the new dividend, and we'll obtain a new remainder, and so on until we reach r sub n minus 2, the second to the last equation, and we have the r sub n minus 1. This r sub n minus 1 will become our new dividend, and the divisor is r sub n. And whenever we reach this r sub n, we will obtain our greatest common divisor. Take note, r sub n is the last non-zero remainder because we say that r sub n minus 1, okay, has a remainder of 0 as clearly shown here. That r sub n minus 1 has a remainder of 0, which we can delete actually. Okay, so that's actually the essence of the Euclidean algorithm. What we'll do is by the successive application of theorem 5, that is by the last theorem that you've talked about, and also the division algorithm, we can actually get the GCD of two big numbers, and that we will discover that it's just equal to the GCD of two smaller numbers, okay, even significantly smaller number. So to give you an example of the Euclidean algorithm in action, so we'll be applying this here. Apply the Euclidean algorithm to find the GCD of 4076 and 1024. Okay, so let's write it here, solution. Okay, so we will be by the successive application of the division algorithm, we get, okay, what do we get? Again, let's put it there. We get that 4076. How many 1024 are there in 4076? Obviously, we cannot reach 4 because that will be 4000. What will that be? Um, 80 something. It's more than 90. So that's only 3. 3 times 1024. What will be our remainder? You can pause the video to get that. But actually, it's 1004. Applying the division algorithm or the Euclidean algorithm, this will become the dividend. This will become the divisor. So what do we have? It's going to become 1024 equals, how many 1004 are there? There's only clearly 1 times 1004. So what's the remainder? So we have 20. 20 as our remainder. Applying the Euclidean algorithm, make this divisor our new dividend, make this remainder our new divisor. What we have is 1004 equals, how many 20s are there in 1004? So to say it to you clearly, that's a lot. Okay, that's actually 50 because 2 times 5 is 10, and then we have 3 zeros, so that's 1000. And then there's a remainder of 4. And then if we're going to continue, this becomes your new dividend, this becomes your new divisor. And what do we have here? This is 20. How many 4s are there in 20? There are 5 4s and 20, and we have 0 remainder. So just to take a look at this, we want this, actually this 4. This is our last non-zero remainder. So take note, if this is our last non-zero remainder by the Euclidean algorithm, okay, so we can say, since 4 is the last non-zero remainder, we can therefore say that the GCD, maybe we can put here, that we can say that the GCD of 4076 and 1024 is equal to 4. And this is our answer for this illustration of the Euclidean algorithm. Since it's the last non-zero remainder, so meaning it's 4. Where did I get this? Going back here, here, in the sequence. So this r sub n is the last non-zero remainder. Therefore, this is equal to the GCD, okay, of the numbers. Okay, so that's the beauty, the elegance of the Euclidean algorithm in finding the greatest common divisor of two such numbers. Okay, so we can see that the algorithm works this way. Okay, the divisor, the old divisor becomes the dividend, the remainder becomes the divisor, and then you so on until you will get the last non-zero remainder, and this non-zero remainder will be your GCD. Okay, so that's the end of the Euclidean algorithm. Thank you very much for watching. I hope you learned something from there, and don't forget to like and subscribe. Okay, thank you very much. See ya.